So what I want to talk about first, I'm going to go a little bit out of order in this chapter. Your book talks about this more first. I want to talk about some equations for heat first, and then we'll come back to the energy equation. So heat. Q is the symbol we use for heat. Why, I don't know. Similar to work, if Q is positive, you're putting energy into the system. If Q is negative, you're taking energy out of the system. Okay. Now we have a couple different equations. We have an equation for heat if it's involved in changing the temperature of the system. And we have an equation for heat if we change the phase of the system. They're different equations because when you change the phase of a material, you're not changing its temperature. Its temperature stays constant. If you're changing the temperature, then the phase isn't changing. The amount of heat necessary to change the temperature of an object, number one, depends upon the mass of the object. The bigger the object is, the more energy will be necessary to change its temperature. Okay. C is called the specific heat. This is something unique to each and every material. Okay. For example, for water, the specific heat is 4,190 joules per kilogram Kelvin. What that means is 4,190 joules of energy are necessary to change the temperature of 1 kilogram of water by 1 Kelvin. So if I had a container with 1 kilogram of water sitting on the table, and I wanted to make the temperature 1 Kelvin higher, I would need to add this much energy, 4,190 joules. Okay. Your book has a table of a few specific heats for a few different materials. It's in no way extensive, but it will have the materials that you're going to need to know. Ice has a different specific heat.
So on that, if you took a degree out, you would get 4,190 joules out of it?
Exactly.
Okay.
Exactly. If you were to decrease its temperature by 1 Kelvin, you will need to take out 4,190 joules of energy. That's exactly right. Now, I should have specified, this is specifically for liquid water. Okay, this is not for ice. This is not if it's vaporized. It's not for gas. It's different for ice. Ice, for example. Let's see. So specific heats are here, and we'll talk about these. So for ice, it's only 2090 joules that are necessary. If you have 1 kilogram of ice and you want to change its temperature by 1 Kelvin, you only need 2090 joules of energy. Okay. Yeah. Right about that. Now, if you look at some of the other materials, the specific heats for some of the other materials aren't nearly as big as it is for water. Water is pretty darn big as far as its specific heat. It's right inside the back cover, so flip all the way inside the back cover to the bottom left-hand table. So the very left side, very bottom table, it has densities and specific heats on it. So if you look at some of the other materials, the specific heat is much smaller. Much smaller. This is why, actually, the climate is so temperate on coastal regions, why the temperature doesn't change by a whole lot in coastal regions. It's pretty nice to live in San Diego, for example. It requires a lot of energy to change temperature. The water absorbs a lot of the energy from the atmosphere, so it keeps the temperature within a fairly decent
So
range.
we just need to build a lot of canals.
There you go.
Or we could turn it into Venice and we're awesome.
Exactly. Sounds good to me. Okay, so the energy needed depends upon mass, specific heat, and how much you want the temperature to change by. So the delta T. Okay. As a side note, just FYI, delta T is the same thing if you do a change in temperature with them in Celsius as if you do them in Kelvin. So you can actually find your delta T by just finding the difference in Celsius degrees, and that will be the same thing as the change in Kelvin. Because in both cases you had to add 273 to both of them. So that's just a side note. Another side note. This equation is any energy involved in changing the temperature of an object, of a material. This doesn't have to be heat. Just like we said, there were mechanical ways to change the temperature of the water in our glass. We could shake it, we could increase the pressure on it, we could stir it. This would still apply, but it wouldn't be heat, it would be work. So this can be work is equal to mcd delta T as well. This is just the energy. However it's done, it doesn't really matter. This is the energy necessary to change the temperature of a material by a certain number of degrees. Change in phase. Energy necessary.
As long as it's in joules. As long as
Correct.
it works in joules, you can do whatever.
Exactly. Now this equation over here, when we do delta T, remember change in anything is final minus initial. So this means T final minus T initial. So if your final temperature is smaller than your initial temperature, you're going to get a negative sign. Q being negative means you took energy out of the system. So this equation will give you the correct plus or minus sign in your delta T. When we deal with the equation for change of phase, the equation itself doesn't give us the proper value, so we have to choose whether it needs to be plus or minus in our particular equation. Okay? The equation, again, it depends upon the mass. It depends upon how much material you have. And then it depends upon what we call the latent heat. L is the latent heat. There's two types of L. LV is the latent heat of vaporization. That's the value if you're going between the solid and the gas or vapor phase. And there's LF, which is the latent heat of fusion. That's between the solid and liquid phase. Inside the back cover, right above that bottom left-hand table, there's a table that has some melting and boiling points and some latent heat values for different materials. The units of latent heat are just joules per kilogram. So it tells us how much energy is necessary to convert 1 kilogram of that material from one phase to another. So for example, for those of you who haven't opened, what is the latent heat of fusion for water? $333,000 joules of energy are required to take 1 kilogram of ice and make it liquid water. A lot of energy is needed. Okay? It only takes 4190 joules of energy to change it by 1 Kelvin. Just to change its phase, a whole lot of energy is needed.
Oh, because it cannot change temperature once it's in that.
When it's in the process of changing phase, it doesn't change temperature.
Well, it makes sense because of that reason. The whole volume doesn't change temperature until it's all the volume of that thing is all changed.
However, if
Exactly.
your ice was at like minus 200 Kelvin, you would have to bring it to phase change first.
Bingo.
with all the energy.
Bingo. So we'd have to use this with the specific heat of ice to get it to 0.
Okay.
And then we would come over here and change its phase and make sure, get it all to liquid water. And then we'd come back over here and increase its temperature to whatever final temperature
So
is.
does it stay within, it's just that, it's just like a constant, like, so 0C is a constant of that phase change. So you'd be at one, you bring it down to 1C, or you bring it down to 0C, and then when you, okay, so which is it?
You bring it down to 0.
Okay.
You have to bring it to its actual
And
melting
then
point.
before it could go to -1.
Correct.
you
You
would have
have
to
to
go
completely
there.
change its phase.
Okay.
Exactly right.